So last time we were talking about nuclear magnetic resonance, and I described the problem. Here is a summary of where more or less we got last time. We said in the setup for nuclear magnetic resonance, we have a large magnetic field. The longitudinal magnetic field is sometimes called, along the z direction. In addition to that longitudinal magnetic field, there's a rotating magnetic field in the xy plane. And it's rotating in the direction that you see here, as seen on the xy plane is clockwise on the plane. In terms of a rotation around the z direction, it's negative, in the sense that a positive rotation around the z plane would go like this. And this magnetic field is rotating in the other direction. So I wrote it here. The magnitude of this radio frequency component is B1, and typically is much smaller than B naught in the problems of interest. Then, as you recall, the spin Hamiltonian is always given by this constant gamma that relates the dipole moment of a particle to its spin angular momentum, B dot S, the S operator. And the S operator has components Sx, Xy, Sz, multiplied by B. Well, the Z component picks up Sz, the X component Sx, the Y component Sy. And this is your Hamiltonian. And as we emphasized last time, this Hamiltonian is time dependent. Moreover, at different times, the Hamiltonian don't commute. So you take Hs at time t1, Hs at time t2, they don't commute. Therefore, any of the formulas we have for solving problems like this don't apply. The only formula that applies is this time-ordered exponential that we spoke about, that in general is very difficult to use. The time-ordered exponential just never quits, and you write terms, term after term, and then you have to add it all up, and adding it all up is difficult. So most of the times it's not a great help. So what did we say we would do? We wondered if we could somehow do quantum mechanics or think of quantum mechanics in the rotating frame, in a frame that is rotating with the magnetic field in such a way that perhaps in that frame the physics would simplify. And physics simplifying would be that the Hamiltonian becomes time independent. So we're trying to figure out how would the Hamiltonian look in another frame. Now, we've not discussed, in general, very explicitly, transformations of Hamiltonians between different frames, but we can sort of roughly try to guess what it would have to do. So what we said last time is that we would imagine that you have an original system and no magnetic field, nothing whatsoever. So forget about all that. No magnetic field. You put the spin state, it stays there forever. Doesn't precess. Doesn't precess because there's no magnetic field. Then you jump into a rotating frame. So this was the static frame, no magnetic field, and then you start rotating. And then you look at the spins, and you know, the spins are not moving, but you say, oh, I'm rotating, so for me, they seem to be precessing. In fact, precessing with the angular frequency that I am rotating. And therefore, in my rotating frame, I would have a Hamiltonian that I would call the rotating Hamiltonian, HR. And how would it look? We claim that, in fact, spin states in my rotating frame would have to be rotating really this way, because I'm rotating with the magnetic field. So for me, they're rotating in the positive z direction with angular frequency omega, and this would be the operator that makes them rotate exactly that way. Because if you remember, an operator here, minus I, angle sz over h bar. This is the angle as a function of time, omega t. That's how these operators rotate states. So this u of t is the u of t that rotates states the way I want them in my rotating frame. Now, you remember, for time-independent systems, the unitary operators e to the minus I h t over h bar. So you identify the Hamiltonian as omega sz. Omega sz. In general, the Hamiltonian of a given a unitary operator, the Hamiltonian is obtained this way. You take the time derivative of it, multiplied by u dagger, and that's the formula for the Hamiltonian, given the time evolution operator, something we did about a couple of weeks ago. So that's where we stood, some idea about a rotating frame. So the way we now make this complete is to say, well, I'm going to attempt to do the following. I'm going to act on with u, this u of t, on this complicated state that I don't know how it behaves. And this I'm going to call the rotated wave function. It's a definition. We're going to use this operator that seems to induce a rotation of the frames and act it on the state to find this. And we're going to hope that the Schrödinger equation for this one is simpler. So actually, last time I actually did the computation and found what is the Schrödinger Hamiltonian for this, psi r. I want to do it in a slightly different way. I think it's a little easier, perhaps, or maybe less familiar but more interesting. I write this like that, u of t, and I say, look, this state evolves due to its own Hamiltonian. U of t is an extra thing I've put here. So here is u of t, but how do I distinguish it? I'll put it s for the spin system, for hs, psi 0. So psi of t is being evolved by the Schrödinger Hamiltonian, the unitary operator associated to the Hamiltonian that we want, times time of 0. So this is the total unitary operator that evolves the state. Therefore, I'm going to say, I'm going to recover the Hamiltonian using this formula. So I will simply say that the rotating Hamiltonian is going to be HR is IH bar dt of this whole thing, u of t, us of t, times its dagger. Because this is the general formula to obtain the Hamiltonian when you know the time evolution operator. So the dagger of this would be us dagger u of t dagger. Now we have to evaluate these derivatives. It's not all that bad. If the time derivative hits the u, this one, then u and u dagger annihilate each other. So you're left with u dagger of t here. So you get IH bar dt u dagger. Now, when it acts on the second one, what do we get? Well, I'll write it this way, plus u of t, because this will be first, then IH bar dt us, and then you have us dagger, and then u dagger of t. Now, this thing is how much? Well, this thing is in fact this Hamiltonian associated to what we call U, which is just omega sz. So actually, I don't know if I have, yeah, I have this notation here. I think it's useful. H of U, the Hamiltonian associated to whatever U it is, so that you get a nice formula, plus U of t, this is the Hamiltonian Hs, U dagger of t. So this formula we derived also last time by looking at the differential equation satisfied by psi r.